Hello, my name is Jeff McNeal, and my co-author, Kevin Vasconcellos, and I would like to share with you our work on policies. Configuring a large, complex test bench can cause a lot of frustration. We generally have a configuration object that gets randomized for each test, so we've got constraints to control the randomization. Often, the people writing tests in an environment are not experts in the internal workings of all the various test bench components, so they don't understand the nuances of their usage. Sometimes, when a test writer finds a set of constraints that do work, those constraints get copied and pasted to all the new tests that they write. Test benches evolve over time. Features get added and modified. If we have lots of copied and pasted code, then we're in a situation where there's more work to do when those changes come. Policies can help alleviate all of these issues. Test writers would like a clear and concise way to control the configuration variables they care about without having to figure out all the interdependencies of the various test bench components. VIP writers and test bench owners would like to have configurations that allow control with minimal programming effort on their part and without having to write a lot of documentation. There are, of course, several approaches to solving this problem. One is to let the user do whatever they would like by exposing the randomized call in the test and then allowing the user to write randomized with constraints. This is simple for the test bench writers, but really tosses the problem into the test writer's lap, as they'll have to solve the randomization failures on their own. Sometimes variables they're trying to constrain aren't even in the top level. They're contained in objects within the configuration objects, which makes constraints hard to do in the randomized with call. We can add helper variables to the configuration object that the test writer can set in order to request that certain features be used. Then the internal constraints can check the value of the helper variable and use it in conditional constraints in multiple places in the configuration object. This works really well for a lot of configurations, but as things get more complex and pieces get more interdependent, the config object complexity can grow and become a management problem in its own right. We end up with several solve before constraints to get our helper variables sorted out before the randomization of member variables happens. A more object-oriented solution is to use children of the configuration object class and add constraints to the children for the configurations that the test writers want. This works well if there's a limited set of combinations necessary, leading to only a few children that are reused in multiple tests. Otherwise, you end up with a lot of children that can be substantially similar but aren't reused. Finally, we can use the policy pattern to package constraints in separate classes, and then the test writer can select what constraint to use at runtime. Wouldn't it be nice to be able to have an easily understandable group of constraints to draw upon that minimize deep understanding of the test bench? Wouldn't it be nice to be able to draw from this group of constraints without having to worry about how things interact with each other? Policies are a way of implementing this kind of methodology. What is a policy? A policy is a container class for a constraint or group of constraints which can be applied to the configuration object at runtime. Think of policies like football players. The red players are the ones in the game, policies that we are using to constrain our test configuration. Blue players represent additional policies or constraints that can be put into play when desired or substituted in for other players. We didn't know of a protocol that the whole audience would know, so we chose to use cars as an example of configuration. Cars have properties that are static. They're chosen when a car is selected, and they have and cars have some controls that can be enabled or disabled each time we drive it. If our tests are going to use a car or a set of cars that we need to randomize, we'll need a configuration object that describes that car, just as your test bench or environment will have a configuration object to be randomized. I'll let Kevin take over from here.
By using policies, we can have an easily understandable list of constraints to draw upon that minimize deep understanding of the test bench. Here, the test writer is aiming to configure a car that is an American-made four-door vehicle with a manual transmission. Pretty clear and concise. Now, let's take a look at how we can accomplish this. Policy library consists of all the policies that can apply to the configuration, the complete team roster from our football analogy. The policy list is a list of policies that are applied to the randomization of the test config for this particular test. There are players in the game, if you will. The policies are selected by the test at runtime and apply their constraints to the variables in the test config. Here is a quick example that extends our car analogy. Shown here are two policies, one to turn the headlights on, the other to turn the headlights off. Instead of having all of the constraints in the configuration object, each constraint is broken out into a policy. Note that each policy class is simply a container for a constraint. Logically, only one of these would be used in a single test. If a mistake is made and both are used, the resulting constraint contradiction is easy to spot and remedy. Using this methodology, a test that doesn't use either of these policies would allow the headlights to be randomized to be either on or off. The idea of using policies for constraints can be attributed to Dickel, as seen in several of his papers. A similar idea was also presented by Nelson. With our origin story complete, let's move on and build the infrastructure. We need to start off with a couple of base classes. Shown here is the policy base class. Note the item member of specialized type item. We'll see this used in a later slide. This provides a reference to the object that we are constraining. Next, we create a policy list class. In common usage, we might get these base classes from a shared or common code directory or common repository. As a convenience and to save some typing, we create typedefs specifically for specializing the base classes to the object we want to apply the policies to. In this case, we are creating typedefs for our test config class policies. Let's write some policies. An easy place to start is with test config member variables that have on-off or enable-disable types of constraints. Typically, these are bit type members or members of an enum type with two values. Here, the test config variable headlights on is of bit type. Each and every constraint will use the form of item.variable because these constraints will be applied to the item or test config in this example. Members that represent multi-valued knobs can also be quickly coded. Note that each of these policies extends the specialized typedef of the base class. Remember, for policies of this category, only 0 or 1 of these will be used at a time. The constraints inside of policies can be arbitrarily complex. Here's a more complicated constraint from a different project dealing with a serial protocol. The encryption type, when encryption is enabled, is related to the selected speed of the DUT, as we can see in the bidirectional constraints. Now let's look into test config object and show how things are put together. We can see the rand member variables or control knobs at the beginning of the class. In this case, my car make, headlights on, and temp setting. Then we see a member of the specialized policy list and a helper string that we'll use in one of the next slides. Finally, we add member variables for each of our defined policies. A few of these policies are lights on, lights off, American, German, and Midwest. Adding policies here makes the job of the test writer easier, as we will soon see. Looking further into test config, an instance of the policy list is created. Since policies are simple containers for constraints, there really is no need to extend them from UVM object, since a set type override doesn't make sense. Instead, the policies are simply created via new and given a sensible, hopefully intuitive name. At the end of the test config new method, we use our helper string to compose a list of all policies available to our test writers. This list can be printed in every test as a convenient way for the test writer to see what policies are available. Policies make use of hierarchical constraints. In order for the policies in the policy list to work on the test config object itself, we need to pass a test config pointer to each of the active policies. This is done in the test config pre-randomize function via the policy list set item function. If we look back at the policy base class, we'd see an item member of our specialized type, which is in turn used as part of each constraint. For example, we saw in the headlights on policy, item.headlightsOn equals 1, which shows us that we are indeed operating on the item test config. We can also print the list of policies in use for randomization so that it is near the potential test config object print. This also aids in debug from just the run log. The list of all policies in use for this test added to the policy list can be printed in post-randomize. The entire list of available policies could also be printed via the helper string seen previously. This is okay for our test config since it is only randomized once. This also puts the print near the test config randomization. A test writer can see what else is available as the list may grow over the course of test bench development. However, we hope that there is an open channel of communication between the test bench writers and the test writers so that new policies don't come as a surprise. Once we have policies, the test writer can choose which policies to use. The test writer can enable or disable certain features or pick a variable value from a list. Features, or variables, with no policy chosen are randomized. Interactions and ordering are handled automatically under the hood. This is the same set of constraints presented earlier. Note that picking German cars must have been specified perhaps in the base test. This is not a problem. Here we see that it is easy to remove an existing, possibly default constraint. This is much easier than disabling an existing constraint. Instead of allowing random origin countries, we pick the American policy to restrict our test to an American car.
Now that Kevin has shown you how to build policies and their infrastructure and how it all fits together, I wanted to highlight one of my favorite aspects of using policies. Here you can see we've got two policies constraining my car make. The first limits us to an American car only. The second policy adds a distribution constraint that attempts to mimic the distribution of cars you might find on a street in a town in the Midwest. When a test selects both policies, they interact seamlessly to produce a distribution of the American cars that you might find in a town in the Midwest. Two simple policies work together without the need for variables or conditionals in order to produce a more complicated result. If a test writer wants to further exclude Fords from the mix, then a trivial policy can be added. Their test can then select this policy in addition to the others to produce the desired distribution. Note that everything else remains untouched. No changes to the Midwest mix policy, the American cars only policy, or the test config base classes. This means there's minimal disruption to the existing test config infrastructure. Because of this, we found that test writers are more likely to add their own policies, which further streamline both their jobs and the test bench writers' jobs. Furthermore, a test can swap out one policy for another. Here we've replaced the Midwest mix with a Northwest mix, a different distribution of car makes, but we've kept the other two policies in place and end up with a completely different mix of cars. You can see how it would be easy to swap out a Japanese car policy for the American car policy to further change our mix. In summary, implementing policies for configuration objects has a lot of benefits. It simplifies constraints because there are fewer helper variables and fewer conditional constraints, which eases the debugging of failures. This simplicity allows non-experts to contribute more easily, both in writing constraints or policies and in writing tests. Policies make it nearly trivial to remove constraints. This means we can allow variables to be completely random or to easily remove constraints we don't want in a particular test. For example, in a special case test like an error injection or debug test. Once the infrastructure is in place, policies simplify adding constraints, even constraints that are only used in a few tests. Multiple policies can add multiple constraints on a member variable, such as a distribution constraint combined with a national origin policy that we just saw above. Have you ever wished you could just get the max and the min values of a member variable in a specific test? Policies make that kind of a task really easy. This can facilitate adding constraints for odd combinations or new features that weren't thought of during the test bench architecture phase. Policies really help to reduce disruptions to the verification team caused by late-stage design or test bench changes. Constraint changes can be easily limited to specific tests while they're in development, or even limited to certain tests on a permanent basis. Tests that use policies provide configuration information at a glance, which can enable quick test auditing to make sure that unwanted constraints weren't accidentally left in a test. Several of our reviewers brought up the same concerns, so we thought we'd address those concerns here. One concern was with ordering of the policies in the policy list. Does the order that the policies are added to the list affect the randomization results? No, it doesn't. Constraints are still solved simultaneously, just like they are when they're all in the base class or when they're all in several child classes. What we did find is that our helper variables went away, which took our solve before constraints with them. Since we didn't have to solve the helper variable for it to influence the configuration member variable, we didn't need the ordering constraints. So policies made ordering less of an issue, not more. The second concern has to do with debugging constraint failures. Was that harder with policies? It turns out that in our case, it became much simpler. The tools that we've used all give a file name and a line number for constraints that caused a conflict. Since all of our policy classes are in separate files whose names match their class names, the error message generally pointed straight to the issue, which was often that we had conflicting policies in the policy list, often as simple as enabling and disabling at the same time. This kind of naming and grouping made fixing these issues trivial. The last concern had to do with implementing a policy-based configuration on an existing test environment. Do you have to convert everything to make them work? Absolutely not. Once the infrastructure is in place, existing constraints can be ported over a few at a time. That's how we did it on our project. Once we got a few simple options ported, we added a few more complex constraints. Then we began to see the simplification benefits and quickly ported many more. In conclusion, implementing policies for test bench configuration provides a simple control mechanism. It reduces the learning curve for new engineers, encapsulates configuration behavior, and allows some settings to be easily overridden or to change other settings. You should go implement policies on your current project right now. We also wanted to point out that policies can be used to randomize any class, but we chose to focus our work on the configuration object and the benefits there. Complete example of all our code can be found on GitHub. Any questions for the live versions of Jeff and Kevin?